Hello friends, welcome back to my YouTube channel. Today I'll continue my discussion on distillation. This will be 26th part of that discussion. And under McAfee method, today I'll be talking about values of the parameter Q for different types of feed to a typical tray column. First, let us understand the working of a typical tray column. A tray column is a cylindrical vessel which has multiple trays in it. Each tray acts as a device where vapor and liquid phases they come in contact with each other. Feed is admitted into the column on a tray that is called feed tray or feed plate. The liquid part of the feed will then flow down. It is taken out at the bottom, sent to a reboiler where it is heated to create a vapor phase. The vapor phase is then admitted into the column at the bottom. It rises through the column. It is taken out at the top. It is then sent to a condenser where it is condensed to get the condensate. The condensate is divided into two parts. One is taken out as the top product. We call that as distillate. The other part of the condensate is sent back to the column. We call that as reflux. The reflux is a liquid that will be flowing down, and then it will join the liquid part of the feed on the feed tray, and the operation continues. The bottom product or the residue, it is taken out from the reboiler. The feed plate divides the column into two sections. The section above the feed plate is rectifying section, and section below the feed plate is stepping section. Then let us know about the types of feed to a typical tray column. The feed to a typical tray column, it is admitted under a variety of thermal conditions, and based on its thermal condition, you have different types of feed. So the feed types based on its thermal conditions, you have 5 different types. First is cold liquid. Then you have liquid at its bubble point, that is saturated liquid. Then you have partially vaporized feed, where it is a mixture, where the feed is a mixture of liquid and vapor phases. Then the fourth type is vapor at its dew point, which is also called as saturated vapor. Here the feed is entirely a vapor. Then the fifth type is superheated vapor, where again the feed is entirely vapor, but this time it is superheated vapor. Okay, so you have this 5 different types of feeds to a typical tray column. Once the feed enters on the feed plate, the quantities of vapor and liquid on the feed plate, they abruptly change. Depending on the type of the feed could be one of these 5 types. So once this feed enters on the feed tray, the quantities of vapor and liquid, they abruptly change on that tray. Then let us understand more about parameter Q. I have already discussed this in my previous videos. You please go and watch those videos. But over here, let us briefly understand what is this parameter Q. The first thing to know about parameter Q is it gives the thermal condition of the feed. Parameter Q, the value of the parameter Q will tell you about the thermal condition of the feed. It is defined by this mathematical equation. Q is equal to Hg minus Hf upon Hg minus HL. Here Hg is molar enthalpy of the vapor phase, Hf is molar enthalpy of the feed, and HL is molar enthalpy of the liquid in the column. What is molar enthalpy? This is enthalpy per unit mole. As per this equation, it will be defined in this way. The heat required to convert 1 mole of feed from its initial condition to saturated vapor divided by the molar latent heat of vaporization. Okay, so in this equation, the numerator is nothing but the heat required to convert 1 mole of feed from its initial condition to saturated vapor. This is the numerator in this equation. And the denominator is molar latent heat of vaporization. Okay, there is another way of defining Q. You have another mathematical equation, which is Q is equal to L bar minus L divided by F. In this case, L bar is molar liquid flow rate in the stripping section of the column. L is molar liquid flow rate in the rectifying section of the column. And feed is the molar, F is the molar flow rate of feed into the column. So as per this definition, or as per this equation, Q will be defined in this way. Q is the moles of saturated liquid resulting in the stripping section per mole of feed that enters the column. Okay, so if you look at the numerator, which is L minus L bar, sorry, this is L bar minus L. So we have the column and the liquid in the rectifying section has molar flow rate of L. And the liquid in the stripping section, it has a molar flow rate of L bar. And if you take a difference between these two, that is L bar minus L, it will be nothing but the saturated liquid that will be resulting in the stripping section when feed is added to the column. Okay, so that's why you have you can also define Q in this way: the moles of saturated liquid resulting in the stripping section per mole of feed that enters the column. So as per this equation, Q will be equal to L bar minus L if F is equal to 1. So if F is 1 mole, then Q will be L bar minus L. Okay, so first let us know what will be the value of Q for cold liquid if the feed admitted to the column is a cold liquid. So when cold liquid is admitted on the feed plate, by cold liquid we mean the feed will be at a temperature that is well below the bubble point of the feed. Bubble point of the feed. So the feed whose temperature is well below the bubble point, well below its bubble point, we call that feed as a cold liquid. So when cold liquid is admitted on the feed plate, what happens? It causes some vapor leaving the feed plate to condense. And the resulting condensate will be then getting added to the liquid in the stripping section. So let us understand that this with the help of a simple schematic diagram. So this is the feed plate, and feed as a cold liquid, it enters. This being entirely liquid, it will be going down into the stripping section. There will be addition of liquid that is coming from the rectifying section. Then you have vapor that is coming from the stripping section to the feed plate. This vapor will be rising from the feed plate, and due to low temperature of the feed, some part of the vapor or some of the vapors, they will be getting condensed, and then the resulting condensate will be adding to the liquid in the stripping section. So this is L dash. Let us say that L dash is the liquid part, or the liquid that is obtained due to condensation. Then in the stripping section, the liquid flow will be addition of this three. One is the liquid that is coming with the feed, then the liquid that is coming from the rectifying section, and the liquid that is obtained or that is resulting due to condensation of some part of the vapor in the rectifying section. Okay. So here L is molar flow rate of liquid in the rectifying section. L bar is molar flow rate of liquid in the stripping section. G bar is molar flow rate of vapor in the stripping section. G is molar flow rate of vapor in the rectifying section. Okay, so by looking at the schematic diagram, you can easily understand L bar is greater than L because there are additions to L to get L bar. That's why L bar is greater than L. And since some of the vapor in the rectifying section is getting condensed, G bar will be greater than G. The molar flow rate of vapor in the stripping section, it will be greater than the molar flow rate in the rectifying section. So you have this relationship. G bar is greater than G. You can easily understand from this schematic. Whatever vapor comes from the stripping section, some of it is getting condensed. That's why G bar will be greater than G. Or you can write it like G is less than G bar. Okay, so I hope the relationships between L bar and L and G bar and G, they are clear to you. Okay, so let me first erase what I have written so that we continue our discussion. Now, the parameter Q, we just understood how it is defined. We'll take this definition. Q is L bar minus L upon F. Now, if you look at the numerator, in the numerator you have L bar minus L. And by looking at the schematic diagram, you can write a simple material balance about the feed plate. So, L bar minus L is equal to the addition of other two liquids, that is liquid in the feed and the liquid that is obtained due to condensation of some of the vapors. Okay, so L bar minus L is, L bar minus L is nothing but F plus L dash. That means it is more than the feed. That is, it is greater than. That means in this defining equation for Q, the numerator is greater than denominator. And that's why Q will always be greater than 1. Okay, so for cold liquid, the parameter Q, it will be having a value that is greater than 1. So this is to be remembered. For cold liquid, the value of the parameter is greater than 1. Why it is 1? You can just understand this in these simple steps. So you can just check the schematic diagram. It will tell you what happens when a cold liquid enters on the feed plate. And then you can easily show L bar is greater than L. And L bar minus L, which is the numerator in this equation, it will be F plus L dash, which is obviously greater than F. That is, numerator is greater than the denominator, and that's why Q will be greater than 1. So henceforth, you will remember this thing. What is that? For cold liquid as a feed to a typical tray column, Q will always be greater than 1. So if somebody tells you the feed to a column has a Q whose value is, say, 1.5, then you can easily tell this feed is a cold liquid. Okay, now let us understand what will be the value, or let us know what will be the value of Q if feed is a saturated liquid. Saturated liquid, it is liquid at its bubble point. So The other way of understanding this is saturated liquid means liquid at its bubble. Saturated liquid or liquid at its bubble point. This is actually liquid solution. Okay. So when saturated liquid is admitted on the feed plate, what happens on the feed plate? Saturated liquid will be entirely liquid, and all of the liquid, it will be getting added to the liquid in the stripping section. As soon as saturated liquid enters the column, it will be getting added to the liquid in the stripping section. So we can understand this with the help of the schematic diagram. So you have the feed plate and feed, which is now a saturated liquid. It is admitted into the column. So all of the liquid will be flowing down. Then you have the liquid that is coming from the rectifying section. It will be adding to this liquid. And this will give you L bar, which will be the molar liquid flow rate in the stripping section. Then the vapor that is rising from the stripping section at a molar flow rate of G bar, it will be simply moving to the feed plate, and then it will be rising from the feed plate. And in the rectifying section, it will be having a molar flow rate of G. So in this case, there will be no change in the molar flow rate of vapor phase, as you can see. So that's why the relationship between L bar and L will be like this. L bar is greater than L. Why? Because the liquid is getting added in the stripping section. That's why L bar is L greater than L. Whereas no change is happening with the vapor phase. That's why molar flow rate of the vapor in the stripping section is equal to molar flow rate of the vapor in the rectifying section, or G bar is equal to J. Okay. Now let us know what will be the value for the parameter Q. So again, we are going to use the defining equation. What is that? Q is equal to L bar minus L divided by F. Now the numerator in this case is, since L bar is greater than L, or you can just look at the schematic diagram, L bar minus L. So if you wish to write material balance for the feed, or just let us write material balance for the liquid across the feed plate. So liquid will be coming along with the feed, and this feed will then add to the liquid that is coming from the rectifying section, and this will be resulting in the liquid in the stripping section. So that means L bar minus L in this case is simply F. That is, the numerator in this case is nothing but F. So you have, for saturated liquid, Q will be F upon F. And that's why for saturated liquid, Q will be equal to 1. And that is what you have to remember. For saturated liquid, Q is equal to 1. How it is 1? I have just told you. So we have simply used this equation to understand or to know that value of Q for saturated liquid is 1. So henceforth, we remember value for the parameter Q when the feed is a saturated liquid, then it is equal to 1. ठीक. Now next, let us know the value for Q if the feed to the J column is partially vaporized. partially vaporized feed, that is, it is a mixture of liquid and vapor phases. Okay, so what happens when partially vaporized feed enters on the feed plate? What changes occur on the feed plate? Simple thing. Liquid part of the feed, it will be getting added to the liquid in the steeping section, and the vapor part of the feed, it will be getting added to vapor in the rectifying section. So if you have to understand this with the help of a simple schematic diagram, let us do that. So you have the feed plate, and now partially vaporized feed is entering the column. So liquid part of the feed, it will be going to the steeping section, and vapor part of the feed, it will be going to the rectifying section. So let the liquid part flow rate of liquid part of the feed into the in the steeping section be L dash, and flow rate of the vapor part of the feed be G dash, molar flow rate. Then you have liquid that is coming from the rectifying section. It will be adding to this L dash, and it will be getting L bar. That means here, if I wish to write a relationship, simple L bar, that is molar liquid flow rate of liquid in the steeping section, it will be addition of L, molar liquid flow rate in the rectifying section, plus L dash, molar liquid flow rate of liquid part of the feed. Okay. Then for the vapor phase, it will be rising from the steeping section at a molar flow rate of G bar, and when it comes in the rectifying section, the vapor part of the feed, that is G dash, will be adding to it to get G. So if we want to write, we can write a relationship. So G, that is molar flow rate of the vapor phase in the rectifying section, is addition of the molar flow rate of the vapor in the steeping section plus molar flow rate of the vapor part of the feed, that is G dash. So you can simply understand from this two relationship, you'll come to know that L bar is greater than L and G bar is less than G. Let me erase this. Okay, before we discuss further, you understand the concept. So you have L bar greater than L because this relationship is true for here, and G bar is less than G, or you can write it like G is greater than G bar. Why? The reason is G is G dash plus G bar. Okay. Now let us use the definition of Q to know its value. So Q is L bar minus L divided by F. And for partially vaporized feed, F is L dash plus G dash, the liquid part and the vapor part. That is, L dash is F minus G dash. And if you use this equation, you have L bar is L dash plus L. L bar is L dash plus L. So now if I use this equation for L dash, or the other way, if I rearrange it, L bar minus L, this will give me L dash. And what is L dash? L dash is F minus G. That is, in the numerator, you have a quantity that is less than F. That means numerator is smaller than the denominator, and that's why Q will be less than 1. Okay, so if you go through once again through the steps, Q is L bar minus L upon F. For partially vaporized feed, you have liquid, mixture of liquid and vapor. So rearranging this gives us L dash as F minus G dash. Whereas in the stripping section, L bar is L dash plus L. That is L bar minus L is L dash. That means as per this definition, L bar minus L is L dash. That is why Q is equal to L dash upon F. But L dash is F minus G dash. So F minus G dash upon F. You have numerator less than denominator. That's why Q will be greater than or less than 1. Okay. It will be never less than 0 for partially vaporized feed. F will not be smaller than G dash because it will have liquid part also. I mean to say that F will always be greater than G dash. And that means F will not be equal to G dash. Okay, so considering these two facts, you can further say that for partially vaporized feed, Q lies between 0 and 1. It will not have a value of 0. It will not have a value of 1, but its value will be lying between 0 and 1. Okay, so what are we supposed to remember over here? For partially vaporized feed, Q is between 0 and 1. It is not 0, it is not 1, but between 0 and 1. Okay, now let us talk about the fourth type of feed, which is saturated vapor. This is nothing but saturated vapor, or you can also understand it as vapor at its dew point. Vapor at its dew point. So if somebody tells you that feed to a column is vapor at its dew point, you should understand that this is vapor, this is saturated vapor. Feed is saturated vapor. That means in this case, the entire feed will be vapor. Okay, so when saturated vapor comes into the column, when it is admitted on the feed plate, all of the vapor, it will be going into the stripping section, rectifying section. That is what will be happening in the tray column. So when saturated vapor or vapor at its dew point is admitted into the column, it will simply add to the vapor in the rectifying section. So we can understand this with the schematic diagram. You have the feed plate, and now F is entering. Since it is saturated vapor, no liquid in it, all of the vapor will be going to the rectifying section. You have liquid that is coming from the rectifying section. It will be simply going to the stripping section. So in this case, you can easily understand nothing is happening with the liquid. Whereas for the vapor that is coming from the stripping section with a molar flow rate of G bar, the vapor, saturated vapor from the feed, it will be adding to it to give G, the molar flow rate of vapor in the rectifying section. Okay, so in this case, L bar is equal to L because nothing is happening to the liquid, and G bar is less than G. Since G, the vapor part of the feed, saturated vapor, which is the feed in this case, it will be adding to the vapor that is coming from the stripping section, and you'll be getting G. That's why G bar will be less than G, or you can say G is greater than G. Okay. So let us use this information to know what is the value of parameter Q in this case. So again, we are going to use this definition for Q. Q is L bar minus L. And you can now easily come to know, since L bar is equal to L, L bar minus L will be 0. L bar minus L is 0. Why it is so? Because in this case, L is equal to L. Okay, that means in this equation, the numerator is 0. So you have Q is equal to 0 upon F, and 0 upon anything is 0. And that's why when you have saturated vapor or vapor at its dew point as a feed to a typical tray column, then value of the parameter Q is 0. So that is what you have to remember in this case. For saturated vapor, value of the parameter Q is 0. Okay, now let us know what will be the value of parameter Q if feed is a superheated vapor. For superheated vapor, the temperature will be greater than the dew point of the vapor. That is the first thing that you have to remember. When you have superheated vapor as the feed, its temperature will be greater than its dew. So when superheated vapor enters the column as a feed, what happens? The entire feed being vapor, all of the vapor will be adding to the vapor in the rectifying section. This is one thing. And due to its temperature, due to the temperature of superheated vapor, what is going to happen? Some of the liquid in the rectifying section, it will be getting vaporized. Okay. And the resulting vapors, then they will be adding to the vapors in the rectifying section. So when superheated vapor is admitted on the feed plate, all of the vapor adds to the vapor in the rectifying section. This is the first thing. Then due to the temperature of superheated vapor, some of the liquid in the rectifying section will be getting vaporized, and the resulting vapors, they will be adding to the vapor in the rectifying section. So you can understand this with the help of this simple schematic diagram. So you have the feed tray, and feed is now entering. Feed being superheated vapor, it will be getting added to the vapor in the rectifying section. And then you have liquid that is coming from the rectifying section. It will be going down. The vapor that is rising from the stripping section, it will be going to the rectifying section. And due to heat of this feed, some of the liquid in the rectifying section, it will be getting vaporized. And all of this vapor will combine to give the molar flow rate for vapor in the rectifying section. So this is the feed. This is superheated vapor. So it is causing some liquid, some part of the liquid in the rectifying section to vaporize. All of this superheated vapor will be going to the rectifying section, and plus you have the vapor that is coming from the stripping section. So in this case, the relationship between L and L bar will be less than L, because some part of the liquid is now converted to vapor. That's why you have a smaller amount of liquid that is coming into the rectifying section. Whereas, since there are two additions to the vapor that are coming from stripping section, G will be greater than G bar. The other way of writing this is G will be greater than G bar. Okay. Now let us know what will be the value for the parameter Q. Again, we will use this definition. Q is L bar minus L upon F. Now in this case, L bar is less than L. Why it is so? I have just told you. And that's why L bar minus L will be less than 0. That means less than 0, that is, it will be a negative value. So in the numerator, you have a negative value. That means Q will also be a negative value. So when you have superheated vapor has a feed to a typical tray column, then value of the parameter Q is less than 0. So over here, you have understood why Q has a negative value for superheated vapor. Okay. So in order to summarize, at the end we will summarize values of Q for various feeds. So for cold liquid, what is the value? Q is greater than 1. For saturated liquid, what is the value? Q is equal to 1. For partially vaporized feed, Q is between 0 and 1. It is not 0, it is not 1, but between 0 and 1. Then for saturated vapor, Q is equal to 0. And for superheated vapor, Q is less than 0. Okay, so with this, I end my discussion. So at the end of this discussion, I'm sure now you'll know what are the values of Q for different types of feed, to a typical tray column. Okay, so with this discussion for today, thank you for being with me. Thanks for watching my videos. Please subscribe to my channel, and you can, there are many videos on distillation. Please watch those videos. Subscribe to my channel. Tell your friends to subscribe to it, and hit the bell icon so that you'll be notified as soon as I upload any new video. For now, have a nice day. Bye bye. Please join me in my next video.